There's something humbling about looking up at the night sky, realizing just how small we are in the grand scheme of the universe. But what if I told you that some of the things we've seen out there don't just inspire awe, they defy explanation? Picture this: a signal from deep space that repeats at random intervals, or a celestial object moving so fast it shouldn't exist according to our current laws of physics. These aren't plot twists from a sci-fi movie. They're real, documented events that have left even the most brilliant astrophysicists scratching their heads. And they're just the beginning. For centuries, we've relied on science to make sense of the cosmos, but the universe loves to surprise us. Some of its most bizarre phenomena refuse to fit neatly into our models, no matter how hard we try. Take fast radio bursts, brief, intense blasts of energy from billions of light years away. We've detected them, but we still don't know what's causing them. Or consider Oumuamua, the first known interstellar visitor, which accelerated in a way that defied gravity's pull. These aren't just gaps in our knowledge, they're glaring reminders that the universe holds secrets we haven't even begun to crack. That's why today we're diving into 24 of the most baffling space mysteries that continue to challenge everything we think we know. From unexplained signals to objects that behave like nothing else in the cosmos, each of these enigmas pushes the boundaries of science. What do they reveal about the limits of human understanding? Could they hint at entirely new physics waiting to be discovered? Strap in, because by the end of this journey, you'll see the night sky not just as a beautiful backdrop, but as a frontier filled with questions begging to be answered. And who knows, maybe one of these mysteries will finally click into place, because sometimes the universe's greatest riddles are just waiting for the right moment to reveal their truth. Let's start with one of the most tantalizing mysteries in the search for extraterrestrial intelligence, the WOW signal. Back in August 1977, a radio telescope in Ohio picked up something extraordinary, a burst of radio waves so powerful, it stood out against the cosmic background noise like a scream in a silent room. The signal lasted 72 seconds, just long enough to catch the attention of astronomer Jerry Amon, who famously scribbled "WOW" in red ink next to the data printout. And then, just as suddenly as it appeared, it vanished. Decades of follow-up searches have turned up nothing, leaving scientists with a haunting question: what was it? The signal had all the hallmarks of an artificial transmission. It was narrow, intense, and centered at a frequency near 1,420 MHz, a quiet spot in the radio spectrum where natural cosmic phenomena rarely emit. This precise frequency also happens to fall within a range considered ideal for interstellar communication, leading some to wonder, was this a deliberate beacon from another civilization? Skeptics point to alternative explanations, like a passing comet or an unusual stellar event, but none fully account for the signal's unique characteristics. Even the most meticulous scans of that patch of sky near the constellation Sagittarius have failed to detect anything like it since. What makes the WOW signal so enduringly fascinating isn't just its mystery, but what it represents. In a universe teeming with natural radio noise, this was a fleeting moment of order, a pattern that felt intentional. Whether it was a cosmic coincidence or a message lost in the void, it reminds us how little we truly know. Every time we point our telescopes skyward, we're left wondering, are we alone, or was the WOW signal our first brush with something or someone else? For now, it remains a cosmic whisper, daring us to listen harder. If the WOW signal left us questioning whether we're alone in the cosmos, the next mystery pulls us into an even deeper existential puzzle, one that shakes the very foundations of how we understand the universe's structure. Imagine looking at a map of the night sky and realizing that countless galaxies, each containing billions of stars, aren't just drifting randomly. They're all being pulled in the same direction, like leaves caught in a cosmic current. This isn't science fiction. It's a real phenomenon astronomers call dark flow, and it defies everything we thought we knew about the limits of our universe. The discovery came from studying the motion of galaxy clusters, some of the largest structures in existence. Scientists expected these clusters to move in a way that aligned with the universe's expansion, a gentle, uniform drift outward from the Big Bang. But when they analyzed data from the cosmic microwave background, the afterglow of the universe's birth, they found something bizarre. Hundreds of clusters were streaming toward a single point in space at speeds exceeding 2 million miles per hour, far faster than any known force could explain. Even stranger, the source of this pull lies beyond the observable universe, in a region we can't see or measure. What could possibly exert such a tremendous gravitational tug on entire galaxies? One theory suggests the existence of a supercluster of unimaginable scale, a structure so massive it warps space-time itself, drawing everything toward it like a magnet. Another, more radical idea proposes that our universe is just one bubble in a vast multiverse, and the dark flow is the gravitational fingerprint of another universe brushing against ours. Both possibilities force us to confront an unsettling truth. There may be realms of reality lying just beyond our cosmic horizon, invisible but undeniably influential. The implications are staggering. If dark flow is real, it means the universe extends far beyond what we can observe, filled with structures and forces we've yet to comprehend. It challenges the long-held assumption that the cosmos is uniform and balanced on large scales, hinting instead at a lopsided, asymmetrical reality. For astrophysicists, this isn't just a curiosity, it's a call to rewrite the textbooks. Every time we think we've mapped the edges of existence, the universe reminds us there's always something more lurking just out of sight. And perhaps that's the most thrilling part of all, not the answers we've found, but the mysteries still waiting to pull us deeper into the unknown. But if dark flow suggests unseen forces tugging at the fabric of our universe, the next mystery brings us to a single, flickering star that behaves like nothing else we've ever observed. Meet KIC 846285, better known as Tabby's star, named after the astronomer who first noticed its bizarre antics. Nestled in the constellation Cygnus, this star doesn't just twinkle gently like its neighbors. It dims in dramatic, unpredictable plunges, sometimes dropping in brightness by a staggering 22% before bouncing back. To put that in perspective, even if a planet the size of Jupiter passed in front of it, the dip would be less than 1%. So what's casting such an enormous shadow? When the Kepler Space Telescope first spotted these erratic dips in 2015, scientists scrambled for answers. The usual suspects, planets, dust clouds, or stellar companions, couldn't explain the star's extreme behavior. The dips were too irregular, too deep, and too asymmetrical. That's when things got wild. One theory proposed a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harvest the star's energy, like a cosmic solar farm. Imagine a network of orbiting panels or habitats so vast they occasionally block the star's light from our view. It's a tantalizing idea, but here's the catch. After years of listening, we've detected no radio signals or other technosignatures that would hint at intelligent design. Natural explanations haven't fared much better. Some suggest a colossal family of comets, shattered planets, or even a warped, dusty ring system could be responsible. Yet none fully account for the star's long-term dimming trend. Its overall brightness has faded by nearly 3% per century, a decline unmatched by any known star. Then there's the alien dust theory, microscopic particles with unusual light-absorbing properties, unlike anything in our solar system. But even this raises more questions than answers. Why would dust behave so erratically? Why here and not around other stars? Tabby's star is more than a cosmic oddity. It's a mirror held up to the limits of our knowledge. Every time we think we've pinned it down, it surprises us again, refusing to fit into any tidy box. Whether it's a natural phenomenon we've yet to understand or something far more extraordinary, one thing's certain: this star reminds us that the universe is still full of surprises, waiting just beyond the edge of our understanding. And that's what makes it so thrilling, not the answers we have, but the ones still just out of reach. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars and planets. Given those staggering numbers, the odds of life emerging elsewhere seem almost inevitable. And yet, when we listen, the cosmos is eerily silent. No signals, no artifacts, no signs of other civilizations. This glaring contradiction is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's a question that haunts astronomers and philosophers alike, because the absence of evidence might be evidence of something far more unsettling. Consider the numbers for a moment. Our Milky Way alone holds an estimated 100 billion stars, with at least one planet orbiting each. Even if only a tiny fraction of those planets are Earth-like, that still leaves millions, if not billions, of potential cradles for life. Given that life arose relatively quickly on Earth once conditions were right, why wouldn't the same happen elsewhere? And if even a handful of civilizations out there developed technology, some should have spread across the galaxy by now. So why do we see no traces of them? Theories abound, but none offer easy answers. One chilling possibility is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar stages. Maybe the filter lies in the past, meaning the leap from simple chemistry to complex life is astronomically rare, or worse, it could still lie ahead of us. If advanced civilizations tend to self-destruct through war, environmental collapse, or unchecked AI, then the silence makes tragic sense. Others suggest that spacefaring societies might simply lose interest in exploration, turning inward to virtual realities or other pursuits we can't yet fathom. Then there's the zoo hypothesis, the idea that extraterrestrial civilizations are aware of us but deliberately avoid contact, treating Earth like a protected wildlife preserve. Or perhaps we're searching the wrong way. What if advanced beings communicate through neutrino beams or quantum entanglement, technologies we're only beginning to grasp? The paradox forces us to confront uncomfortable truths. Either we're alone, which feels statistically improbable, or we're not, which raises the question, what's keeping everyone hidden? The Fermi Paradox isn't just about aliens, it's a mirror reflecting our own fragility and ambition. Every time we scan the skies and hear nothing, we're left wondering, are we the first, the last, or simply missing something profound? Until we find an answer, the silence remains one of the universe's most haunting mysteries, reminding us that the greatest enigma might not be the stars themselves, but what or who isn't there. Just when you think space can't get any stranger, along comes a phenomenon that makes even seasoned astronomers do a double take. Fast radio bursts, or FRB, are like the universe playing an endless game of cosmic Morse code. These blasts of radio waves pack more energy than the sun emits in months into just milliseconds, and they come from galaxies billions of light years away. But here's the real kicker. Some of these bursts fire once and disappear without a trace, while others repeat in erratic, unpredictable patterns. It's as if the cosmos is teasing us, dropping clues but refusing to reveal the full story. The first FRB was detected in 2007, buried in archived data from a radio telescope in Australia. At first, scientists thought it might be a glitch, a blip from Earth-bound interference. But then more bursts appeared, each one arriving from deep space with no obvious explanation. The mystery deepened in 2016 when astronomers stumbled upon a repeater, FRB 121102, a burst that flickered on and off like a malfunctioning beacon. Unlike its one-time cousins, this one kept coming back, sometimes firing off multiple bursts in an hour before going silent for months. What could possibly power such bizarre behavior? The leading theory points to magnetars, highly magnetic neutron stars that occasionally unleash apocalyptic flares. Picture a spinning stellar corpse, its magnetic field so intense it twists spacetime itself. When the star's crust cracks under pressure, it might release a burst of energy visible across the universe. But not all FRBs fit this mold. Some repeaters flare with clockwork precision, while others seem to cluster in active periods followed by eerie silence. Then there's FRB 2019-20818, a burst from a spiral galaxy surprisingly similar to our own Milky Way, but originating in a region with no obvious stellar fireworks. If magnetars are responsible, why do they behave so differently from one another? And then there's the elephant in the room. Could some FRBs be artificial? The idea isn't as far-fetched as it sounds. A sufficiently advanced civilization might use focused energy beams to power interstellar probes, like a cosmic lighthouse guiding ships across the void. The burst's intensity and brevity match what we'd expect from directed energy technology. Even the repetition could make sense if it's a targeted signal rather than a natural eruption. Of course, most scientists lean toward astrophysical explanations, but the sheer variety of FRBs leaves room for possibility. After all, ruling out the extraordinary requires extraordinary evidence, and right now we're still grasping at cosmic straws. What makes FRBs so captivating isn't just their mystery, but what they reveal about the universe's hidden chaos. These bursts travel billions of years to reach us, carrying whispers from galaxies so distant their stars have long since burned out. With every new detection, we're handed another piece of a puzzle we don't yet know how to solve. Are they the death cries of collapsing stars, the hum of alien engines, or something we haven't even dreamed of? For now, the cosmos keeps its secrets close, firing off these enigmatic signals like a siren call, daring us to listen, to wonder, and to keep searching. We've seen how mysterious forces can pull entire galaxy clusters across the cosmos, but there's something even closer to home that's warping our local galactic neighborhood, and we can't even see it. Lurking about 250 million light-years away, hidden behind the thick dust clouds of our own Milky Way's galactic plane, lies an immense gravitational force astronomers call the Great Attractor. Picture this: our galaxy isn't just drifting aimlessly through space, it's being hauled toward this enigmatic region at over 1 million miles per hour, dragging hundreds of other galaxies along with it. Whatever lies there must be unimaginably massive, yet because it sits directly behind the busiest part of our own galaxy, it's like trying to spot a lighthouse through a blizzard. The discovery dates back to the 1970s, when astronomers mapping cosmic motions noticed something peculiar. Instead of scattering evenly as the universe expands, galaxies in our corner of space share a peculiar drift, all moving toward the same invisible point in the constellation Centaurus. This wasn't just random noise. The sheer number of galaxies caught in this flow suggested a gravitational anchor of staggering proportions. calculations show the Great Attractor would need the mass of tens of thousands of Milky Ways packed into a relatively small space to exert such a pull. But when telescopes scanned that region, they found nothing matching that description, just a hazy patch of interstellar dust blocking our view. Here's where it gets even stranger. As technology improved, astronomers peered deeper and realized the Great Attractor might just be the tip of the cosmic iceberg. Beyond it lies something even more colossal, the Shapley supercluster, a sprawling metropolis of galaxies containing nearly 10,000 times the mass of our Milky Way. Could this be the true source of the pull? Maybe, but the math still doesn't quite add up. Even Shapley's immense gravity can't fully explain the velocities we're seeing, suggesting there's still something else lurking in that obscured zone, something we've yet to identify. Theories range from concentrations of dark matter so dense they bend spacetime like a cosmic whirlpool, to exotic large-scale structures we don't yet have names for. Some speculate about a dark flow connection. Perhaps this motion ties into the same mysterious forces pulling distant galaxy clusters. But until we develop telescopes that can peer through the Milky Way's dusty veil, the Great Attractor remains a ghost in our cosmic equations, a reminder that sometimes the biggest mysteries aren't in the distant cosmos, but hidden in plain sight just out of view. What's thrilling is how this invisible heavyweight challenges our cosmic perspective. We often think of galaxies as island universes drifting apart in the expanding void. Yet here we are, caught in a river of stars, all flowing toward something we can't see. It's humbling proof that even in our own galactic backyard, the universe keeps its most astonishing secrets tucked just beyond the light we can see, waiting for the day our curiosity and technology finally pull back the curtain. Of all the cosmic surprises that have drifted into our solar system, none have sparked as much intrigue or controversy as Oumuamua. This strange, tumbling object made history in October 2017 as the first confirmed visitor from another star system. But from the moment telescopes spotted it racing past the sun at nearly 200,000 miles per hour, nothing about it made sense. Its trajectory was too straight, its speed too fast, and its shape, well, that was the first clue this wasn't just another space rock. Most asteroids and comets in our solar system are roughly spherical or lumpy, shaped by billions of years of collisions. Oumuamua broke all the rules. Observations suggested it was at least 10 times longer than it was wide, a cosmic cigar tumbling end over end through the void. Then came the real shocker. As it zoomed away from the sun, instead of slowing down as expected, it sped up. Comets sometimes accelerate like this when their icy surfaces vaporize, creating a natural rocket effect. But Oumuamua showed no visible coma or tail, no telltale signs of outgassing. So what gave it that extra push? The mystery deepened when astronomers realized how unusually reflective it was. Its surface brightness varied dramatically as it spun, suggesting either an elongated metallic object or one covered in strange, light-scattering material. Some researchers proposed it could be a hydrogen iceberg, a chunk of frozen hydrogen so pristine it left no trail as it vaporized. Others imagined a fractal-like, a dust bunny structure, fragile and porous, forged in some exotic stellar environment we've never seen. But each explanation had holes. Hydrogen ice should have vaporized long before reaching us, and fragile structures rarely survive interstellar journeys intact. Then came the most provocative theory: could Oumuamua be artificial? Astronomer Avi Loeb famously suggested it might be a light sail, a thin, discarded relic of alien technology pushed by starlight. The idea wasn't entirely far-fetched. Humanity has already launched prototype light sails like Japan's Ikaros probe, but without definitive proof, the scientific community remained divided. Mainstream astronomers pointed to more mundane possibilities, like unseen outgassing or unusual solar radiation effects. Yet even these couldn't fully explain its acceleration without leaving traces we should have detected. What makes Oumuamua so endlessly fascinating isn't just its oddities, but what it represents: a fleeting glimpse into the diversity of cosmic objects we've barely begun to catalogue. Most interstellar visitors probably go unnoticed, tiny, dark, and fast. That we spotted this one at all was pure luck. Its brief appearance forced us to confront how little we know about what lurks between the stars. Was it a shard of a shattered planet, a weird comet defying our expectations, or something even more extraordinary? Unless another interstellar traveler drops by for study, Oumuamua's secrets may forever remain as elusive as its origins, a ghostly reminder that the universe is far stranger than we dare imagine. Some mysteries cling to the public imagination like cosmic static, persistent, crackling with intrigue, and nearly impossible to ignore. Case in point, the Black Knight satellite, a shadowy object said to be silently circling Earth for thousands of years, watching us with unknown intent. The legend paints it as an alien artifact, a relic from an advanced civilization that might have been studying humanity long before we ever looked up. But here's where fact and science fiction collide, because while the stories are electrifying, the truth might be far more ordinary. The tale began in the late 1950s, when newspapers reported strange radio signals supposedly coming from an unknown satellite orbiting Earth. At the time, only two nations had launched anything into space: the Soviet Union with Sputnik and the United States with Explorer 1. So when amateur radio operators claimed to detect something else up there, imaginations ran wild. Could it be extraterrestrial? The myth snowballed when a photograph from the 1998 Space Shuttle Endeavour mission appeared to show a dark, irregular object against Earth's curvature. Conspiracy theorists pounced, declaring it proof of the Black Knight's existence. But let's rewind for a reality check. Astronomers and satellite trackers have identified the object in that photo as likely being a thermal blanket lost during a spacewalk, a mundane piece of human-made debris drifting in orbit. As for those eerie radio signals, they were probably natural cosmic noise or early satellite transmissions misinterpreted in the pre-digital era. Even Nikola Tesla, who some claim intercepted the Black Knight signals in the early 20th century, was more likely picking up pulsars, distant, rapidly spinning neutron stars that emit regular radio pulses. Yet here's the twist: the Black Knight myth persists because it taps into something deeper than just a misidentified piece of space junk. It speaks to our fascination with the idea that we're not alone, that some intelligence, ancient and advanced, might be silently observing us. The myth's endurance also highlights how easily the vast, cluttered expanse of Earth's orbit can become a canvas for our wildest speculations. With over 27,000 tracked pieces of debris circling our planet, it's no wonder a few have sparked legends. Could there be a sliver of truth buried beneath the layers of lore? Unlikely, but that doesn't make the mystery any less compelling. Sometimes the stories we tell about the cosmos reveal more about us than they do about the universe. The Black Knight isn't just a satellite, it's a mirror reflecting our eternal hope and fear that somewhere out there someone might be looking back. And until we can scan every inch of our orbital backyard, that tantalizing uncertainty will keep the legend alive, floating just beyond the edge of proof. Imagine looking at a baby picture of the universe, a snapshot taken just 380,000 years after the Big Bang, and spotting a blemish so stark it shouldn't exist. That's exactly what astronomers found in the cosmic microwave background, the faint glow left over from the universe's fiery birth. Stretching nearly 2 billion light-years across, an eerie cold spot lingers like a cosmic bruise, defying every expectation of how matter and energy should be distributed. Temperatures there dip significantly lower than the surrounding regions, as if some invisible hand reached into the early universe and scooped out a chunk of its heat. This isn't just statistical noise, it's a gaping anomaly that challenges our most fundamental models of cosmology. When scientists first mapped the CMB in detail using satellites like WMAP and Planck, they expected minor fluctuations, tiny variations that would eventually seed the galaxies and voids we see today. But the cold spot was different. Its temperature deviation is so extreme that the odds of it occurring randomly are about 1 in 50, unlikely enough to raise eyebrows but not impossible. However, when combined with its bizarre lack of surrounding galaxy clusters as if the spot repelled matter, the probability plummets to 1 in 200,000. Suddenly, coincidence stops being a satisfying explanation. So what could carve such a colossal chill into the fabric of the cosmos? One radical theory suggests we're seeing the fingerprint of a collision with another universe, a bubble beyond our own, brushing against ours in the multiverse's foam. Picture two soap bubbles gently touching. At their meeting point, energy might have drained away, leaving behind this cosmic cold spot. It's a breathtaking idea, but not without critics. Skeptics argue that exotic physics within our own universe, like a supervoid, an enormous empty region of space stretching across the cold spot, could explain the temperature drop. Yet even supervoids struggle to account for the spot's sheer scale and its peculiar gravitational effects. Then there's the quantum entanglement hypothesis. Some theorists propose that the cold spot marks where our universe's quantum fields tangled with another during inflation, the rapid expansion moments after the Big Bang. If true, it would mean the spot isn't just a curiosity, it's a window into physics operating at energies we can't possibly recreate on Earth. Others float even wilder ideas, like a defect in spacetime itself, a cosmic knot left over from the universe's birth, warping the space around it. What makes the cold spot so electrifying isn't just the theories it inspires, but what it reveals about our place in the grand scheme of reality. If it truly is evidence of a multiverse, we're forced to confront an unsettling truth. Our universe might be just one page in an infinite cosmic library. Or perhaps it's something even stranger, a flaw in our understanding of gravity, thermodynamics, or the very nature of spacetime. Every time we think we've grasped the universe's rules, anomalies like this whisper, there's more to learn, more to question, more to wonder about. And that's the real magic, not the answers we have, but the mysteries that keep pulling us deeper into the unknown. We think we know what the universe is made of until we actually count it up, and the numbers refuse to add up. Here's the problem. When cosmologists tally all the normal matter, the protons, neutrons, and electrons that make up stars, planets, and us, they come up astonishingly short. Based on the universe's earliest light, the cosmic microwave background, we know roughly how much baryonic matter should exist. But when we look around at galaxies and gas clouds today, nearly half of it is missing. That's right, somewhere out there, an amount of material equal to tens of billions of Milky Ways has simply vanished without a trace. So where did it go? The leading suspect, vast, invisible rivers of superheated gas threading between galaxies. Picture steam so thin it's practically a ghost, stretching millions of light years across intergalactic space. These filaments, part of the so-called warm-hot intergalactic medium or WIM, are thought to contain the universe's missing matter, but detecting them is like trying to spot a candle flame in a fog bank. The gas is too diffuse to emit much light and too hot to absorb it in ways our telescopes easily see. For decades, it was like searching for smoke without fire. Then, in 2017, a breakthrough. astronomers used the European Space Agency's XMM Newton telescope to study a distant quasar, a brilliant beacon whose light passes through these cosmic cobwebs on its way to Earth. By analyzing how the quasar's light dimmed at specific X-ray wavelengths, they found fingerprints of highly ionized oxygen, a telltale sign of the WIM's searing hot gas. Similar studies since have mapped more of these filaments, slowly filling in the gaps. But here's the catch: even after accounting for these discoveries, we're still missing about 30% of the expected matter. Some theorists suggest the answer lies in even hotter gas, heated to temperatures above 10 million degrees by shock waves from colliding galaxy clusters. Others propose that ultra-fast particles called cosmic rays or elusive neutrinos might carry a fraction of the missing mass. Then there's the wild card. Could some baryons be hiding in exotic forms we haven't yet imagined, locked inside primordial black holes or woven into strange quantum states? The closer we look, the more the universe seems to play a shell game with its own building blocks. What makes this mystery so profound isn't just the missing matter itself, but what it reveals about the limits of our cosmic senses. Every galaxy, every star, every atom we can see might just be the tip of an invisible iceberg floating in a sea of matter so subtle it's evaded detection for billions of years. Solving this puzzle isn't just about accounting for lost atoms. It's about rewriting our understanding of how the universe structures itself on the grandest scales. And until we find that last 30%, we're left with a humbling truth. Even the stuff we're made of is still full of surprises. Sometimes the most baffling discoveries come not from distant galaxies, but from our own cosmic backyard. In the 1970s and 80s, as NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt toward the outer solar system, engineers noticed something peculiar. These trailblazing probes, which had already delivered stunning images of Jupiter and Saturn, began slowing down ever so slightly more than physics predicted. At first, the discrepancy seemed trivial, just a fraction of a nanometer per second squared, but over decades of travel, that tiny anomaly added up. By the time Pioneer 10 crossed Neptune's orbit, it was hundreds of miles off course. The numbers didn't lie. Something was tugging at these spacecraft, and no one could explain why. Theories erupted like solar flares. Could it be the gravitational pull of unseen dark matter clumped near our solar system? Or perhaps a glitch in the probe's own design, heat radiating from their nuclear power sources, nudging them off course like a gentle breeze on a sail? Engineers meticulously modeled every possible variable, from the spacecraft's aluminum wiring to the faint pressure of sunlight itself. Yet even after accounting for these factors, the Pioneer's deceleration stubbornly remained. Then came the real curveball, when scientists analyzed data from other distant missions like the Galileo and Ulysses probes. They found no similar anomaly. If this was some fundamental flaw in our understanding of gravity, why weren't all spacecraft affected? The mystery deepened further when New Horizons, launched in 2006, showed no sign of the Pioneer anomaly at all. It was as if whatever had tugged at the Pioneers had simply stopped. Some physicists proposed radical solutions, like modifications to Einstein's theory of general relativity at extremely weak gravitational fields. Others wondered if the anomaly hinted at unseen dimensions or quantum gravity, effects too subtle to detect on Earth. But the most likely explanation turned out to be the most mundane: thermal recoil. In 2012, a team analyzing decades of telemetry data concluded that heat from the Pioneer's electrical systems, radiating unevenly off their dish-shaped antennae, could have generated just enough thrust to explain the drift. Case closed? Not quite. Even this thorough analysis left tiny discrepancies unaccounted for, leaving room for whispers of something stranger. What makes the Pioneer Anomaly so compelling isn't just the mystery itself, but what it represents. A humbling reminder that even in our own celestial neighborhood, the universe keeps secrets. Whether it was a quirk of engineering or a fleeting glimpse of new physics, those two small probes taught us a vital lesson. Sometimes, the biggest discoveries come from paying attention to the smallest deviations. And out there in the dark, who knows what other anomalies might be waiting just beyond the edge of our equations? Just when we thought Tabby's star was the universe's most baffling light flicker, along comes another celestial oddball that makes even its erratic dimming look tame. Meet KIC 8462852, a star so mysterious it doesn't even have a catchy nickname yet. Located roughly 1,500 light-years away in the constellation Cygnus, this star doesn't just dip in brightness occasionally. It plunges into darkness with drops so dramatic they'd make an eclipse look like a gentle blink. We're talking dips of up to 20%, far deeper than any known planet could cause, and in patterns so irregular they leave astronomers scrambling for explanations. The first clues emerged when volunteers with the Planet Hunters Project, a citizen science initiative sifting through Kepler Space Telescope data, spotted something bizarre. While most exoplanet discoveries hinge on predictable, repeating dimming from orbiting worlds, this star's light curves were chaotic. Some dips lasted days, others weeks, with no discernible rhythm. Even stranger, its overall brightness wasn't constant. Over Kepler's 4-year mission, the star's light output declined steadily, dimming by nearly 3% before suddenly plummeting another 15% in one dramatic event. Imagine a light bulb that not only flickers randomly but also grows fainter over time, except this bulb is a massive, raging ball of fusion-powered plasma. So what's casting such an enormous shadow? The usual suspects, planets, comets, or stellar companions, don't come close to explaining the scale of these dips. A Jupiter-sized planet would block less than 1% of the star's light, and even a swarm of comets would struggle to produce such extreme, erratic patterns. That's led some researchers to revisit the idea of alien megastructures, hypothetical constructs like Dyson swarms that could harvest a star's energy. The notion isn't entirely science fiction. Humanity has already sketched blueprints for similar technology. But here's the catch. Follow-up observations haven't found the telltale infrared glow such structures should emit as waste heat. If it's alien engineering, it's unlike anything we've ever imagined. Natural explanations haven't fared much better. One theory suggests a colossal collision, perhaps two planets smashing together, creating a sprawling debris field that occasionally eclipses the star. Another posits a family of super-sized dust clouds, their particles oddly sized or shaped to block light in these peculiar ways. Then there's the ringed gas giant hypothesis, a planet with Saturn-like rings, warped by gravitational tugs into a jagged, light-absorbing maze. But each of these struggles to explain the long-term fading. Why would dust or debris stick around for years, steadily accumulating? The most compelling clue might lie in the star's own behavior. Unlike Tabby's star, which is relatively ordinary, KIC 8462852 belongs to a rare class called F-type stars, hotter and more massive than our Sun. Some astronomers speculate its wild light patterns could stem from internal instability, with violent magnetic storms or plasma eruptions hurling material into space. Picture a star throwing tantrums, ejecting thick shrouds of gas that temporarily veil its light. Yet even this can't fully account for the dip's sheer depth and irregularity. What makes this star so electrifying isn't just the mystery, it's the way it defies every category we try to stuff it into. with Tabby's star, we at least had a handful of plausible theories. Here, the data refuses to cooperate, dancing just out of reach of every explanation we throw at it. Whether it's an astronomical phenomenon we've never witnessed or something far more extraordinary, KIC 8462852 forces us to confront an exhilarating truth. The universe is still writing its rulebook, and every bizarre discovery is another page waiting to be read. If the cosmic microwave background is the universe's baby picture, then the so-called axis of evil is the unsettling glare in that photo, a pattern so bizarre, it makes cosmologists question everything they thought they knew about randomness. This isn't just a minor quirk, it's a colossal alignment in the CMB's temperature fluctuations that stretches across the sky like a cosmic equator, defying the fundamental assumption that the universe should look the same in all directions. When scientists first spotted this eerie symmetry in data from the Wilkinson Microwave Anisotropy Probe and later the Planck satellite, it sent shockwaves through the field. Because if the universe began in a chaotic Big Bang, why would its oldest light carry the ghostly imprint of order? The numbers tell the story. In a perfectly random cosmos, temperature variations in the CMB should scatter like confetti. No preferred direction, no hidden structure. Yet when researchers analyzed the data, they found hot and cold spots aligned along a specific axis, with odds of it happening by chance estimated at less than 1 in 1,000. It's as if someone took the universe's fingerprint and smudged it deliberately. Some theorists dismissed it as a statistical fluke, a cosmic mirage that would vanish with better data. But the Planck mission's sharper measurements only deepened the mystery. The axis persisted, stubborn and unexplained. Explanations range from the unsettling to the revolutionary. One possibility, our solar system's motion through space might be contaminating the data, like static distorting a radio signal. As Earth orbits the Sun and the Sun orbits the galaxy, we're hurtling through the CMB at about 370 kilometers per second. This movement could theoretically stretch temperature fluctuations into false patterns. But here's the catch: when scientists corrected for this motion, the axis of evil remained. Another idea suggests gravitational waves from the universe's inflationary period might have twisted space-time in a way that left this peculiar mark. Yet even this elegant theory struggles to explain the axis's precise alignment. Then there's the mind-bending alternative. What if the universe isn't as isotropic as we've assumed? Cosmology's bedrock principle, the cosmological principle, states that on large scales, the universe should appear uniform no matter where you look. But the axis of evil whispers a heretical question. What if it's not? Could the universe have a preferred direction, a fundamental asymmetry woven into its fabric? Some speculative models even propose that the axis hints at a pre-Big Bang structure, a relic from some earlier phase of existence that imprinted itself onto our cosmos like a shadow. What makes this mystery so gripping isn't just the potential scientific upheaval, but the philosophical weight it carries. If the axis is real, it means our universe might be less random, less neutral than we've always believed. It's a reminder that even our most cherished assumptions about reality are provisional, waiting to be appended by the next anomaly. Whether it's a measurement error, a quirk of physics, or something far more profound, the axis of evil challenges us to wonder: are we reading the universe's deepest secrets, or just seeing patterns in the cosmic static? For now, it remains one of cosmology's most tantalizing open questions. A silent enigma written across the sky, daring us to decode it. Most of the universe looks like a crowded metropolis, galaxies clustered together in sprawling superclusters, woven into vast cosmic webs. But then there's the Boötes Void, a staggering bubble of nothingness so vast it defies comprehension. Picture a sphere 330 million light-years wide, containing just 60 or so galaxies where there should be thousands. If the Milky Way sat at its center, humanity wouldn't have discovered other galaxies until the 1960s. That's how empty this place is. Astronomers call it the Great Nothing, and its existence rips a hole straight through our understanding of how the cosmos structures itself. The void was first spotted in the 1980s when surveys mapping galaxy distributions revealed a glaring gap in the constellation Boötes. At first, scientists assumed it was an error, a trick of incomplete data. But the deeper they looked, the more unsettling it became. This wasn't just a small, empty pocket. It was a cosmic desert spanning 1% of the observable universe. For perspective, if the average distance between galaxies were a mile, the Boötes Void would be like finding a gap the size of Australia. The odds of such a void forming naturally. Less than 1 in a million. So how did this emptiness come to be? One leading theory blames quantum fluctuations from the universe's infancy, tiny ripples in density that, during inflation, stretched into gargantuan voids. Think of blowing up a balloon with microscopic wrinkles. When it expands to cosmic scales, those wrinkles become vast valleys. But even this can't fully explain the Boötes Void's extreme sparseness. Another idea suggests it's the aftermath of multiple smaller voids merging over eons, like soap bubbles combining into one colossal emptiness. Yet simulations struggle to reproduce anything quite this barren. Then there's the wild card. Could something or someone have cleared this space? The notion isn't as far-fetched as it sounds. A hypothetical Type 3 civilization, capable of harnessing the energy of entire galaxies, might dismantle stars and planets on a staggering scale, leaving behind a void. While there's zero concrete evidence for this, it's a chilling thought experiment. After all, if advanced life exists, wouldn't it seek to maximize resources, or even rearrange the cosmos to its liking? But perhaps the most haunting possibility is that the Boötes Void isn't unique. Smaller voids pepper the cosmos, and some researchers speculate this one might be part of a vast, nested structure, a fractal pattern of emptiness repeating across scales. If true, it would mean the universe isn't just lumpy. It's organized in its hollowness, with voids within voids like cosmic matryoshka dolls. What makes the Boötes Void so mesmerizing isn't just its scale, but the questions it forces us to confront. Is it a fluke, a fingerprint of deeper physics, or something even stranger? In a universe that tends toward chaos, this eerie expanse of nothingness feels almost deliberate, as if the cosmos is daring us to look deeper, to question not just what's there, but what isn't. And until we solve its riddle, the Great Nothing will loom as a silent reminder of how much we have yet to understand. Among the swirling chaos of the cosmos, where nebulae typically resemble splattered paint or ethereal ghosts, one structure stands out with almost artificial precision: the Red Rectangle Nebula. Nestled about 2,300 light-years away in the constellation Monoceros, this cosmic gem isn't just another cloud of gas and dust. From our vantage point, it forms a near-perfect geometric shape, a glowing, crimson-hued X framed by what appears to be a rectangular border. It's as if the universe, known for its wild, untamed beauty, decided to draft this nebula with a ruler and protractor. The story begins with HD 44179, the aging binary star system at the heart of the nebula. One star has already shed its outer layers, while its companion dances close enough to shape those ejections into something extraordinary. Most dying stars create spherical or spiral nebulae. Think of the ring nebula's smoke-like halo or the cat's eye's intricate swirls. But the red rectangle defies convention. Its symmetry is so precise, early astronomers suspected imaging artifacts or optical illusions. Only later observations confirmed this structure is real and it's utterly unique. So how does a star produce such architectural perfection? The secret lies in the interplay between the two stars and a thick, dusty disk encircling them. As the primary star sheds material, its companion star's gravity funnels that outflow into two opposing cones. From our perspective, these cones intersect, creating the illusion of an X. Meanwhile, the disk's edges scatter light, tracing the nebula's rectangular frame. It's a cosmic fountain sculpted by gravity and chance, a fleeting masterpiece that will vanish in a few thousand years as the stars complete their dance. But the mysteries don't stop at its shape. The red rectangle's vibrant color, a deep, rusty red unlike the usual blues and greens of nebulae, comes from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons. These complex organics, nicknamed stardust, are the same compounds found in soot and interstellar space. Their presence here in such abundance hints at the building blocks of life being forged in the death throes of stars. The nebula's geometric elegance challenges our assumptions about stellar death. We've long assumed these processes were messy and chaotic, yet the red rectangle proves that under just the right conditions, nature can craft something shockingly orderly. It's a reminder that the universe has a flair for the unexpected, capable of creating both breathtaking chaos and precision that rivals human art. And as this stellar duo continues its slow-motion waltz, we're left to wonder, how many other cosmic wonders hide in plain sight, waiting for us to adjust our lenses and our expectations? The moon hangs in our sky like a silent sentinel, a familiar presence we often take for granted. But beneath its cratered surface lies a puzzle that rewrites what we thought we knew about planetary magnetism. Today, our moon is a quiet, barren rock with no global magnetic field. Yet, samples brought back by Apollo astronauts tell a different story, one where the moon once crackled with magnetic energy, rivaling Earth's own protective shield. This revelation sends shockwaves through planetary science because, by all accounts, the moon is far too small to have ever generated such a field on its own. Here's the conundrum: planetary magnetic fields are born from churning molten metal in a core, a process called a dynamo. For a dynamo to work, you need heat, motion, and time, ingredients Earth has in spades thanks to its massive molten iron core. The moon, though, its core is tiny, just a fraction of its total size, and without the internal heat or convective forces to sustain a magnetic powerhouse. Yet lunar rocks dating back billions of years bear the unmistakable imprint of a strong magnetic field, one that lasted for hundreds of millions of years before mysteriously fading away. So what sparked this lunar dynamo against all odds? One leading theory points to a cosmic catastrophe, the moon's violent origin itself. The prevailing giant impact hypothesis suggests the moon formed when a Mars-sized body, nicknamed Theia, slammed into the early Earth, flinging debris into orbit that coalesced into our moon. That collision might have left the newborn moon molten and turbulent, its core spinning wildly like a top. If the impact tilted the moon's axis just right, it could have set off a temporary dynamo, a magnetic field fueled by chaos rather than steady internal motion. But there's a catch. While impacts can jolt a core into action, they're usually short-lived. The moon's field persisted for eons, far longer than any collision could explain. That's led scientists to explore another possibility: tidal heating. Early in its history, the moon orbited much closer to Earth, and our planet's gravitational pull stretched and squeezed its interior like putty. This constant flexing could have kept the lunar core simmering, churning its metals just enough to sustain a dynamo. It's a delicate balancing act: too little heat, and the dynamo sputters; too much, and the core solidifies. Yet somehow, for a brief cosmic moment, the moon struck gold. Then there's the wild card. Could the moon's crust hold the key? Some researchers propose that massive asteroid impacts in its youth didn't just leave craters. They supercharged the dynamo by sloshing the core like a stirred drink. Others speculate about exotic materials in the lunar interior, like radioactive elements that decayed and heated the core from within. But every explanation comes with holes. If impacts powered the field, why did it last so long? If tides were the engine, why did the dynamo die when the moon drifted only slightly farther away? The moon's magnetic past isn't just a lunar curiosity. It's a window into the hidden lives of small, rocky worlds. If something as modest as the moon once hosted a robust magnetic field, what does that mean for exoplanets we've dismissed as too small to shield life? Could magnetic flickers be common in the universe, flaring up under the right conditions before vanishing into the dark? For now, the moon keeps its secrets locked in ancient rock, a silent witness to forces we're only beginning to understand. And as we prepare to return to its surface with new missions, one thing's certain: the quieter a world seems, the louder its past might whisper. Deep in the heart of our galaxy, where stars crowd together like fireflies in a jar, there's a glow that shouldn't exist, an eerie excess of gamma rays radiating from the Milky Way's core. Discovered by NASA, a Fermi Gamma Ray Space Telescope, this mysterious emission bathes the galactic center in high-energy light, defying all expectations. The puzzle isn't just what's causing it, but why it's so concentrated, so symmetrical, and so stubbornly unexplained. Some whisper it could be the smoking gun for dark matter, the universe's most elusive substance. Others argue it's something far more mundane, yet equally hidden. Either way, the galactic center excess isn't just a scientific curiosity. It's a cosmic riddle wrapped in gamma-ray enigma. At first glance, the culprit seems obvious. The galactic center is a chaotic place packed with pulsars, black holes, and supernova remnants, all capable of producing gamma rays. But when scientists tallied up the known sources, the numbers didn't add up. The excess glow is too smooth, too evenly distributed, almost as if something invisible is saturating the region with energy. That's where dark matter enters the scene. Theorists have long predicted that when dark matter particles collide, they might annihilate each other in bursts of gamma radiation. If true, the galactic center excess could be our first tangible clue to this shadowy substance that makes up 85% of the universe's mass. But here's the twist: not everyone's convinced. Alternative explanations point to a hidden population of millisecond pulsars, rapidly spinning neutron stars too faint to detect individually, but collectively capable of producing the glow. These cosmic lighthouses, relics of dead stars, emit gamma rays as their powerful magnetic fields whip particles to near light speeds. The catch: even the most sensitive telescopes struggle to spot enough of them to account for the excess. It's like hearing a choir but only seeing a handful of singers. Where's the rest of the chorus? The debate rages on, fueled by tantalizing hints and frustrating dead ends. Some researchers argue the glow's spatial distribution matches dark matter models too perfectly to ignore. Others counter that the pulsar theory gained traction when Fermi spotted similar excesses in other galaxies, suggesting a more universal astrophysical process. Then there's the wild card. Could it be both? A mix of pulsars and dark matter, their signals tangled together in a way we can't yet untangle. What makes this mystery so electrifying isn't just the science, it's the stakes. If the excess is dark matter's fingerprint, it would revolutionize physics, finally cracking open the secrets of the universe's hidden architecture. If it's pulsars, it means our galaxy's core harbors thousands of undiscovered stellar ghosts, rewriting the story of stellar evolution. And if it's neither, well, that's the most exciting possibility of all, because sometimes the universe's greatest gifts aren't the answers we expect, but the questions we never saw coming. We think we've grasped the scale of the universe until discoveries like the Hercules Corona Borealis Great Wall come along and shatter every expectation. This isn't just another supercluster or cosmic filament. It's a mind-bending behemoth, a sprawling tapestry of galaxies stretching an almost incomprehensible 10 billion light-years from end to end. To put that in perspective, if you could travel at the speed of light, crossing this structure would take more than twice the current age of Earth. And yet, here's the real kicker. This colossus existed when the universe was barely half its present age. How could something so vast assemble so quickly, defying everything we know about cosmic evolution? The discovery came in 2013, when astronomers mapping gamma-ray bursts, the universe's most violent explosions, noticed an eerie pattern. These bursts weren't scattered randomly. They traced an arc across the sky, marking the outlines of a structure so enormous it shouldn't exist. According to the cosmological principle, the universe should look roughly uniform on scales larger than about 1.2 billion light-years. But the Great Wall dwarfs that limit nearly tenfold, like finding a single mountain range spanning an entire continent. It's not just big, it's impossibly big, forcing us to question whether our models of the early universe are missing something fundamental. So how does a structure this size emerge from the primordial cosmos? One theory suggests it's a fossil of inflation, the universe's exponential growth spurt in the first fractions of a second after the Big Bang. Tiny quantum fluctuations stretched to cosmic proportions could have seeded regions of slightly higher density, blueprints for future megastructures. But even inflation struggles to explain the wall's sheer scale. Another idea points to dark matter's invisible scaffolding, whose gravity might have funneled ordinary matter into these vast, thread-like formations. Yet simulations of dark matter behavior rarely produce anything as extreme as Hercules' Corona Borealis. Then there's the radical possibility: what if the wall isn't a structure at all, but a shadow? Some theorists propose it could be the imprint of a collision between our universe and another bubble in the multiverse, a cosmic bruise left by a long-ago encounter. Others wonder if we're seeing the remnants of a phase transition, like cracks in space-time frozen during the universe's cooling. But these ideas, while thrilling, lack concrete evidence. The wall remains a paradox, too large to ignore, yet too anomalous to explain. What makes this discovery so exhilarating isn't just its scale, but what it reveals about our place in the cosmos. For centuries, we've assumed the universe was fundamentally smooth on grand scales, a vast, featureless expanse dotted with islands of matter. The Great Wall turns that assumption on its head, hinting at a cosmos far lumpier and more intricate than we ever imagined. It's a humbling reminder that every time we think we've mapped the limits of reality, the universe paints outside the lines, leaving us to wonder what other colossal secrets might be hiding in plain sight, just waiting for the right moment to reveal themselves. Imagine a world where the ground beneath your feet isn't rock or ice but diamond, not just scattered gems but a planet-sized chunk of crystallized carbon glittering in the eternal darkness of space. Meet PSR J1719-1438b, better known as the Diamond Planet, a celestial oddball orbiting a pulsar about 4,000 light-years from Earth. Discovered in 2010, this planet isn't just rare, it defies everything we thought we knew about how planets form and what they're made of. This cosmic jewel began as a star itself, once part of a binary system. When its companion star went supernova, the explosion blasted away its outer layers, leaving behind a dense, spinning corpse called a pulsar, a neutron star that beams radiation like a lighthouse. The remaining core, now stripped to its essence, was likely once a white dwarf, an Earth-sized ember of a dead star. But here's where things get wild. Under the pulsar's intense gravitational pull, the white dwarf's carbon-rich interior may have been crushed into a crystalline structure, transforming it into a planet-sized diamond. The numbers are staggering. This planet is roughly 5 times Earth's mass, yet only about half its diameter, making it denser than any known world. If you could weigh a sugar cube-sized chunk of this place, it would tip the scales at thousands of pounds. But how do we know it's really diamond? Spectroscopic analysis of the pulsar's radio pulses revealed subtle distortions caused by the planet's gravity, allowing scientists to estimate its composition. The data points to a carbon-dominated world, with oxygen and other elements scrubbed away by the supernova's fury. Under such extreme pressure, carbon doesn't just become diamond. It might form exotic crystalline states we can't even replicate on Earth. What makes this planet truly mind-bending isn't just its composition, but its origin story. Most planets form from the dusty leftovers of a star's birth, coalescing in protoplanetary disks. The diamond planet, though, is a cosmic phoenix born from stellar death and destruction. It challenges the very definition of a planet, blurring the line between planet and stellar remnant. Could there be others like it? Almost certainly. Pulsars are common in the galaxy, and if this one has a diamond companion, others might too. Yet the real treasure here isn't the hypothetical gemstones, it's the insight into planetary diversity. For centuries, we assumed planets fell into neat categories: rocky worlds like Earth, gas giants like Jupiter, or ice dwarfs like Pluto. The diamond planet shatters those boxes, proving the universe is far more creative than we imagined. It raises tantalizing questions. Are there planets made of sapphire or graphite? Could extreme pressures forge even stranger materials we've never seen? This glittering enigma is more than a cosmic curiosity. It's a testament to the universe's ability to surprise us. Every time we think we've seen it all, along comes a world that turns our assumptions to stardust. And as we keep searching the skies, who knows what other impossible planets might be waiting, hidden in the dark, rewriting the rules one discovery at a time. For all the stars, galaxies, and cosmic wonders we can see, they're just the tip of the iceberg floating atop an invisible ocean of something far more mysterious. Dark matter, the unseen scaffolding of the universe, outweighs ordinary matter 5 to 1, sculpting galaxies into shape and bending the fabric of space-time itself. Yet here's the catch: despite decades of searching, we've never directly caught a single particle of it, not one. This isn't just a gap in our knowledge, it's a cosmic-sized riddle that forces us to question whether we're missing a fundamental piece of reality. The first clues emerged in the 1930s, when astronomer Fritz Zwicky noticed something bizarre about the Coma galaxy cluster. The visible stars and gas simply didn't have enough gravity to hold the cluster together. It should have flown apart long ago. Something unseen was gluing it together, something Zwicky called Dunkel Materie, dark matter. Decades later, Vera Rubin's observations of spinning galaxies confirmed it. Stars at the edges of galaxies whirled just as fast as those near the center, defying Newton's laws unless some invisible mass was tugging on them. The verdict was clear: the cosmos is teeming with matter we can't see. But what is it? The leading candidate is WIMP, weakly interacting massive particles, hypothetical bits of exotic matter that barely interact with light or ordinary stuff. Think of them as cosmic ghosts, passing through Earth by the trillions every second without leaving a trace. Scientists have built ultra-sensitive detectors deep underground, shielded from cosmic noise. hoping to catch a faint bump against an atomic nucleus. So far, silence. Other experiments, like the Large Hadron Collider, have smashed particles at near light speeds, searching for dark matter's fingerprints in the debris. Still nothing. That's led some physicists to consider an even wilder possibility. Maybe dark matter isn't a particle at all. Modified Newtonian dynamics, or MUND, suggests that gravity itself behaves differently on cosmic scales, eliminating the need for invisible matter. It's a radical idea, one that rewrites Einstein's equations, but it explains some galactic motions surprisingly well. Yet MUND struggles with larger phenomena, like the way dark matter bends light around galaxy clusters in gravitational lensing. The truth might lie somewhere in between, an undiscovered particle and tweaks to gravity, a cosmic two for one we've yet to untangle. Then there's the darkest horse of all, primordial black holes. These hypothetical relics, forged in the chaos of the Big Bang, could be lurking everywhere, their collective gravity masquerading as dark matter. Some might be as small as asteroids, others as massive as stars, all invisible unless they distort starlight or collide catastrophically. The James Webb Space Telescope could soon spot their telltale warping of distant light, offering the first tangible clues. What makes this enigma so thrilling isn't just the mystery, it's the stakes. Dark matter isn't some fringe curiosity. It's the universe's hidden architecture, the unseen hand guiding everything from galaxy formation to the fate of the cosmos. Every time we think we're close to an answer, it slips through our fingers like shadow. Whether it's a particle waiting to be discovered, a flaw in our theories, or something beyond our wildest imaginings, one thing's certain: solving the dark matter puzzle won't just fill a gap in our equations, it'll rewrite the story of the universe itself. And that's the beauty of science. Sometimes the most profound truths are the ones we can't yet see. The cosmic microwave background is often called the universe's baby picture, a near-perfect snapshot of its infancy. But in that snapshot, there's a blemish so vast it stretches the limits of plausibility. Spanning an astonishing 1.8 billion light-years across, the Eredana Supervoid isn't just an empty patch of space. It's a cosmic desert so barren, its sheer size defies the laws of probability. And here's where it gets eerie. This void doesn't just exist. It appears to be cooling the universe's oldest light in a way that challenges our fundamental understanding of reality. When astronomers first mapped the cosmic microwave background in detail, they expected tiny temperature fluctuations, cosmic wrinkles left over from the Big Bang. But the Eredana Supervoid stood out like a frozen thumbprint. The CMB's temperature dips noticeably in this region, as if something drained its energy long ago. At first glance, that makes sense. Fewer galaxies mean less matter to gravitationally tug on photons, leaving them slightly colder. But here's the catch. The void's size and the CMB's temperature drop don't align with standard cosmology. According to our models, a void this massive should leave a far subtler imprint. The discrepancy is so stark, some researchers wonder if we're missing a crucial piece of physics. One radical theory suggests the supervoid might be a portal to something beyond our universe, a cosmic bruise left by a collision with another bubble in the multiverse. Picture two soap bubbles grazing each other. At the contact point, energy could have leaked away, leaving behind this frigid expanse. Others propose a flaw in Einstein's theory of gravity itself. Modified gravity models, like emergent gravity, attempt to explain the anomaly by tweaking how mass bends spacetime on cosmic scales. But even these can't fully reconcile the void's extreme properties. Then there's the simplest explanation: the supervoid isn't special at all. Skeptics argue it might just be a statistical fluke, a random overdensity of smaller voids lining up by chance. Yet simulations show the odds of such a perfect alignment are vanishingly small. And if it is a fluke, why does it align so neatly with other cosmic anomalies, like the mysterious cold spot in the CMB? What makes the Eredana Supervoid so captivating isn't just its size, it's the way it forces us to question the universe's rulebook. Is it a sign of exotic physics, a window into the multiverse, or just a cosmic illusion? Until we peer deeper into its emptiness, this colossal blank spot in the sky will remain one of cosmology's most tantalizing riddles, a silent challenge to everything we think we know. Black holes are cosmic monsters gaping voids in space so massive, not even light can escape their grasp. We often imagine them as colossal beasts lurking at the centers of galaxies, or the remnants of exploded stars scattered across the cosmos. But what if I told you there's a black hole practically in our backyard, one so small, so peculiar, it barely fits the mold of what we thought black holes could be? Meet the unicorn, a black hole just 1,500 light-years from Earth, tucked quietly in the constellation Monoceros. The unicorn earned its name not just for its rarity, but for the way it was discovered. Unlike most black holes, which reveal themselves by violently devouring nearby stars or emitting X-rays, this one was found by its subtle gravitational tug on a neighboring red giant star. Astronomers noticed the star's light rhythmically stretching and compressing, as if an invisible companion were pulling it in a slow, cosmic dance. The culprit. A black hole no more than 3 times the mass of our Sun, tiny by black hole standards, and shockingly close to home. This discovery turns our understanding of black hole formation on its head. Stellar mass black holes are usually born from the explosive deaths of massive stars, collapsing under their own gravity. But stars that small aren't supposed to form black holes at all. They typically fade into dense neutron stars or white dwarfs. So how did the unicorn defy the odds? One theory suggests it might be the stripped-down core of a once larger star, its outer layers siphoned away by a companion over billions of years. Another possibility is that it formed through an entirely different process, perhaps merging neutron stars or some exotic collapse we've yet to imagine. And here's the real kicker. If the unicorn exists, there could be dozens, even hundreds of similar black holes hiding in our galactic neighborhood, invisible except for their gravitational whispers. Traditional detection methods would miss them entirely, leaving us blind to a potential population of cosmic phantoms drifting between the stars. That raises a spine-tingling question. Could one of these unseen objects be even closer than we realize, silently shaping the motions of stars we've known for centuries? What makes the unicorn so mesmerizing isn't just its existence, but what it implies. For decades, black holes were thought to exist only in extreme environments, violent, chaotic corners of the universe. Now we know they could be lurking in the quiet places too, rewriting the rules of where and how they form. It's a reminder that sometimes the most extraordinary discoveries aren't just about finding something new, they're about realizing how much we've overlooked. And in the vast, uncharted stretches of our own galaxy, who knows what other cosmic unicorns might be waiting just out of sight? Just when astronomers thought they'd catalogued every type of structure the universe could throw at us, along came something so bizarre it was literally named for what it is because nobody could figure out what else to call it. Meet the odd radio circles, or ORC, faint, gargantuan rings of radio waves spanning hundreds of thousands of light-years, floating in deep space like cosmic smoke rings with no apparent source. Discovered in 2019 by Australia's ASCAP radio telescope array, these ghostly halos are so perplexing that the team who found them spent months convinced it had to be an instrument glitch. But the circles were real, and their existence throws yet another wrench into our understanding of how galaxies evolve. What makes ORCs so baffling isn't just their shape, but what's missing from the picture. Most dramatic cosmic events like galaxy collisions or supermassive black hole eruptions leave behind visible wreckage, twisted stellar debris, glowing gas clouds, or blazing quasars. ORCs show none of that. They're nearly invisible in optical, infrared, and X-ray wavelengths, appearing only in radio observations. It's like finding the ripples from a pebble dropped in a pond, but with no pebble and no pond, just perfect circles hanging in the void. The largest ORC discovered so far could swallow 10 Milky Ways side by side, yet whatever created it left no trace we can detect. Theories range from the explosive to the exotic. One leading idea suggests ORCs are the aftermath of titanic galactic mergers, shockwaves from two supermassive black holes spiraling together, sending out spheres of energy that appear as rings from our perspective. Another posits they're the faded remnants of dead radio galaxies, their jets having switched off eons ago, leaving behind echo chambers of radio waves. But both explanations struggle with the ORC's perfect circularity and lack of central disturbance. If these were merger remnants, why don't we see any distorted galaxies at their hearts? Then there's the more speculative possibility. ORCs could be windows into entirely new physics. Some researchers suggest they might be the signatures of cosmic strings, hypothetical spacetime defects left over from the Big Bang, or even the wakes of unimaginably powerful dark matter interactions. The most tantalizing and controversial theory proposes that ORCs are spherical shock waves from advanced civilizations, not as deliberate signals, but as byproducts of energy harvesting technologies operating on galactic scales. While there's zero concrete evidence for this, it underscores how thoroughly these structures defy conventional explanation. What makes ORCs more than just another cosmic curiosity is their potential to rewrite the rules of galactic ecology. If shockwaves from mergers or black hole activity can persist as coherent rings for millions of years, it would mean the universe is crisscrossed with invisible boundaries we've only just begun to notice. They might even explain why some regions of space seem suspiciously empty. Perhaps ORC-like events cleared them out long ago. With each new discovery, these enigmatic circles challenge us to reconsider not just what we see in the cosmos, but what we might be missing. And as radio telescopes grow more sensitive, one thing's certain: the universe always finds new ways to remind us that for every answer we uncover, a dozen new questions take its place. There's a number so fundamental to cosmology that it's practically written into the universe's blueprint, the Hubble constant. It tells us how fast the cosmos is expanding, the very pulse of reality itself. For decades, astronomers have refined this value, confident that no matter how you measure it, the answer should converge. But here's the unsettling truth: it doesn't. Depending on where you look and how you calculate it, the universe's expansion rate changes not by a little, but by enough to send scientists back to the drawing board. This discrepancy, known as the Hubble Tension, isn't just a minor hiccup in the data. It's a full-blown crisis that could upend our understanding of everything from the Big Bang to the fate of the cosmos. The conflict arises when two gold standard methods clash. The first approach studies the cosmic microwave background, the afterglow of the Big Bang, using it as a cosmic yardstick to extrapolate the universe's expansion over 13.8 billion years. The second method relies on standard candles, pulsating stars called Cepheids, and cataclysmic supernova, whose known brightness lets us gauge distances to nearby galaxies. Both techniques are meticulous, both have been cross-checked relentlessly, yet they stubbornly disagree. The CMB method suggests an expansion rate of about 67 kilometers per second per megaparsec, while local measurements hover around 73. That gap might seem small, but in the precise world of cosmology, it's a chasm. At first, researchers assumed someone had made a mistake, a miscalibration in telescope optics, perhaps, or an overlooked variable in supernova physics. But after years of double-checking, the tension only tightened. Teams recalibrated instruments, scrubbed data for biases, even launched new telescopes like the James Webb Space Telescope to settle the debate. Yet the numbers refused to align. That's when a more thrilling possibility emerged. What if the discrepancy isn't an error at all, but a signpost to new physics? One radical explanation involves dark energy, the mysterious force accelerating the universe's expansion, behaving differently than we thought. Maybe it's not constant, but evolving, growing stronger or weaker over time. Alternatively, there could be an unknown particle, like a dark radiation, subtly tweaking the early universe's dynamics. Some theorists even speculate about modifications to Einstein's gravity itself, suggesting that the laws governing the cosmos might change across vast distances or epochs. The wildest ideas flirt with multiple bubbles of space-time, where our local universe expands slightly faster than the broader cosmos, a cosmic anomaly wrapped in a larger, slower-moving whole. The Hubble tension isn't just academic, it's a fork in the road for cosmology. If it's a calibration issue, it means our tools need refining. But if it's new physics, we're on the brink of a revolution. One that could rewrite the story of the universe's birth, evolution, and ultimate destiny. Every time we think we've pinned down the cosmos's rules, it throws us a curveball, reminding us that the universe is far stranger, far more dynamic than we ever imagined. And until we crack this puzzle, the Hubble tension stands as a humbling testament to how much we still have left to learn. From unexplained signals to hidden cosmic structures, these 24 mysteries are more than just scientific curiosities, they're invitations to wonder. Each one challenges us to rethink what we know, proving that the universe is far stranger, far more dynamic than our textbooks ever suggested. Whether it's the haunting silence of the Fermi Paradox or the cosmic tug-of-war of dark flow, these enigmas aren't just gaps in our knowledge. They're doorways to discoveries we haven't even imagined yet. Think about it. Every time we've encountered a cosmic mystery, solving it has reshaped our understanding of reality. The bizarre orbit of Mercury led Einstein to general relativity. The faint glow of the cosmic microwave background revealed the Big Bang's echo. Today's puzzles, like the Hubble tension or the ghostly whispers of fast radio bursts, could be the keys to tomorrow's breakthroughs. They push us to build better telescopes, sharper simulations, and bolder theories. And sometimes the most thrilling part isn't the answer itself, but the journey to find it. So which of these cosmic riddles captivates you? Is it the diamond planet glittering in the void, or the Great Attractor pulling us toward the unknown? Maybe it's the eerie precision of the Red Rectangle Nebula, a masterpiece painted by stellar winds. Whatever sparks your curiosity, remember, these mysteries belong to all of us. They're reminders that science isn't just a collection of facts, it's an ongoing conversation, a collective effort to peel back the layers of the universe. The best part, we're just getting started, with missions like the James Webb Space Telescope probing deeper into space and time, and AI sifting through mountains of data. The next decade could bring answers, or even better, new questions. So hit subscribe and join us as we keep exploring, because the cosmos isn't done surprising us yet. And who knows, the next great discovery might be hiding in plain sight, waiting for someone like you to look up and wonder.